The purpose of a light vehicle transmission is to transmit engine torque to the driving wheels. It also has to provide for this torque to be increased or decreased to suit differing road and operating conditions. In a manual transmission, this is done by the driver manually selecting gear ratios to suit. In an automatic transmission, it is done by both the transmission control system automatically selecting the gearing according to load and speed, and by the torque converter. The torque converter is mounted on the engine in the same place as a manual clutch and does the same job, transmitting engine torque to the input shaft of the transmission. It can also multiply torque according to driving conditions. It's a fluid coupling, with the fluid acting as the driving medium, since none of the converter components are physically connected to the others. It acts as an automatic clutch. At engine idle speeds, it allows the engine to operate while the vehicle is stationary and the transmission is in a drive range. In its simplest form, a single-stage torque converter has three elements: the impeller, the turbine, and stator. All three have angled or curved vanes and are contained in a single casing. They are separated from each other by thrust bearings, but maintain a close relationship for efficient torque transmission. The impeller has a large number of vanes attached to the converter case to form the driving member. The vanes rotate with the casing as the engine rotates. Each one has a slight curvature and is set radially in the case. The turbine is similar in construction to the impeller, but with more vanes and with a greater curvature. The direction of curvature of the turbine vanes is opposite to that of the impeller vanes. The turbine is free to rotate in the casing, and a central spline mates with a spline on the input shaft. When the fluid coming from the impeller rotates the turbine, the transmission input shaft also rotates. Both the impeller and the turbine are fitted with a torus or guide ring. This helps to secure the vanes in position. It also reduces turbulence at the center to improve efficiency. The stator has a small set of curved blades attached to a central hub and is positioned between the impeller and the turbine. The central hub is mounted on a one-way clutch splined to a stator support shaft and fixed to the transmission case. The one-way clutch allows the stator to rotate only in the same direction as the impeller. Trying to rotate the stator in the opposite direction locks the stator on the support shaft and holds it stationary. In the Sprague-type one-way clutch, the inner race has a central spline. It locates on the stator support shaft to hold the race stationary. The outer race is part of the stator hub. It turns with the stator in the direction of engine rotation. Equally spaced sprags between the two races produce a wedging action to stop the stator rotating in reverse. The sprags are held in place by a spring-loaded cage. The cage moves the sprags together so that when the stator is locked, each carries an equal share of the load. The one-way action is produced by the different radii of the sprags and the curvature at their outer edges. This gradually increases from the shorter radius to the larger. When the stator is turned against engine rotation, it pivots the sprags towards the larger radius and wedges them between the two races, locking them together. When the effort to the stator is reversed, the sprags pivot towards the smaller radius and the outer race glides freely over them in the direction of engine rotation. In the roller-type one-way clutch, the inner race is splined to the stator support. The outer race has wedge-shaped segments, which retain the rollers. In each segment, a waved compression spring pushes each roller towards the narrow end of the wedge. A force on the stator blades against engine rotation locks the outer race onto the rollers, wedged between the two races. Turning the stator with the engine rotation eases the wedging, and the stator rotates with the impeller and turbine. In a lock-up converter, the impeller and turbine are locked together when conditions are suitable to provide a one-to-one drive from the engine to the transmission input shaft. Lock-up normally occurs at higher road speeds when light throttle openings are being used. The lock-up piston engages in slots in the turbine and can move axially for engagement and disengagement. Torsional damper springs are built into the turbine piston assembly. When the clutch is engaged, these springs dampen driveline and torsional vibrations. When the clutch facing on the piston comes in contact with the internal machine surface on the wall of the converter housing, lockup occurs. This provides a one-to-one connection from engine to transmission with no slippage between components. When the engine starts and idles, the transmission pump rapidly fills and pressurizes the converter. The impeller is driven by the engine and turns at crankshaft speed. With the selector lever in the neutral or park position, the turbine also rotates, carried around by momentum of the fluid. When a drive position is selected, the turbine shaft is locked to the transmission output shaft through the transmission gearing, and the turbine comes to a halt. Centrifugal force throws fluid between the impeller vanes outwards, around the back of the guide ring in a forward direction. This is due to the shape of the casing and the curvature of the vanes. With the engine idling and the vehicle stationary, little torque is transferred from impeller to turbine as the fluid flow is too gentle. When the engine accelerates, higher impeller speed discharges the fluid across and against the turbine vanes with greater force. Fluid exits the impeller at high velocity and enters the turbine at its outer edge. This exerts a turning effort against the back of the turbine vanes, which absorbs energy in the fluid, causing the turbine to rotate and transfer the drive to the transmission. The fluid, still at high velocity, now flows between the turbine vanes, leaving the turbine in a direction opposite to impeller rotation. This is due to the curvature of the turbine vanes. Unchecked, this would oppose impeller rotation and reduce turning effort. To defeat this, the stator redirects the fluid. It re-enters the impeller in the same direction as impeller rotation. The fluid strikes the forward face of the stator blades with a backward force, which locks the stator on the one-way clutch. The stationary stator and the angle of the blades change the direction of the fluid flowing between them. The fluid re-enters the impeller at high velocity in the same direction as impeller rotation. It strikes the back of the impeller vanes with considerable force, giving up energy to assist the engine in turning the impeller. This provides torque multiplication. Torque multiplication exists only when there is a difference in speed between the impeller and the turbine. The magnitude of torque multiplication depends on load. When the turbine is stalled, it has a maximum value of about 2.2 to 1. Stall is an operating condition where the turbine is stationary and the engine throttle is wide open, making the rotational speed of the impeller as high as possible. Stall can be approximated to when a vehicle moves from rest up an incline, towing a heavy caravan or car trailer. Instantaneously, as the vehicle begins to move, maximum torque multiplication occurs. At an engine speed of 2,100 RPM and torque at that speed of 100 Newton meters, the torque input to the transmission will be 2.2 times that value, 220 Newton meters. This multiplication tapers off as the turbine commences to turn and increases in speed. This subjects the fluid in the turbine passages to centrifugal force, which slows down the circulation between impeller and turbine. When turbine speed reaches around 90% of impeller speed, torque multiplication falls to zero. Torque transfer from impeller to turbine is then about 1 to 1. This is known as the coupling point. At coupling point, fluid flow from the turbine vanes is relatively low, but it is at high speed in the direction of rotation. The rapidly turning turbine discharges its fluid against the back of the stator blades. This force unlocks the stator and all three elements rotate as one unit. Unlocking the stator prevents turbulence in the fluid and any braking effect on the engine. The revolving impeller carries the fluid with it inside the converter casing. The fluid is rotating around the axis of the converter. This is known as the rotary flow. At the same time, centrifugal force moves the fluid outwards, away from the converter axis. During torque multiplication, the shape of the converter case makes the fluid flow in a circular motion through the impeller, turbine, and stator. This is known as the vortex flow. Combining these two fluid flows produces a progressive circular or spiraling motion. This is known as the spiral flow. In a stalled converter, fluid flows at high velocity from the revolving impeller through the stationary turbine and stator. This results in a fast-moving vortex flow and high torque multiplication. When the turbine starts to rotate and increases in speed, the centrifugal force on the fluid in the turbine opposes the high velocity flow from the impeller. This reduces vortex flow and torque multiplication. At coupling point, the vortex flow of fluid is slight, and there is no torque multiplication. The converter now acts as a fluid coupling. During acceleration or hill climbing, torque needed by the drive shaft can exceed the engine output torque. As a result, the turbine slows, causing an increase in vortex flow. This again causes torque multiplication. The converter automatically adjusts its output within design limits to meet drive shaft requirements. Converter slip and loss of power through the transmission produces heat, which must be dissipated. At stall, a lot of engine output is converted into heat, and this brings the oil operating temperature closer to its boiling point. Excessive temperature rise can produce cavitation bubbles in the fluid, which produces noise and reduces converter efficiency. Some converters use external fins on the case to circulate air through the housing onto the converter. Most automatic transmission vehicles use a heat exchanger in the lower tank of the radiator. Fluid flows from the pump to the converter, then through the heat exchanger before returning to the transmission.